years, right before he left Exxon, and kept doing it, and we felt that it would be a useful technique to probe some of the cobalt Fischer-Tropsch questions that we had. And we had a very talented student who is now with H-Power, Chris Bertoli. So I'm going to show you some results from that collaboration. Let me just quickly flash the picture of the process we are talking about. We start with natural gas, and then natural gas is converted into synthesis gas, carbon monoxide and hydrogen mixture, which then in a Fischer-Tropsch synthesis is converted into a high carbon number hydrocarbons, which then needs to be upgraded in order to make it a useful product either as lube or fuel. The major objective of the process is make as much heavy hydrocarbon products as we can, because those are the high volume yet high value products that can be on a large scale sold in the market. We just did an evaluation on the basis of some patent art, and made a comparison how our current AGC21 catalyst performs against the prior art. And as you can see, it is, I'd say, a factor of several higher performing than even our best catalyst during the 1980s. So progress is continuously being made, and I'm going to show you how the details of that progress came about. Just very briefly, I don't think that this audience needs a lot of introduction to this, but again, the chemistry is oxygen, methane, and steam are reacted to make the CO and hydrogen in a proper stoichiometry. That is then used on a cobalt catalyst in the AGC21 process, converted into mostly waxy hydrocarbons with very high ASF alpha, which then is being hydroisomerized to make it a liquid product. We have catalytic processes in all proprietary catalytic processes in all three process steps. I'm going to talk about today about the middle step, the Fischer-Tropsch process, and I'm going to show you how the process and the chemistry on the surface interacts, and how then those interactions need to be taken into account as you devise the process or as you try to optimize the process, increase activity and yields. The first example, I go back to what we started with, the iron catalyst. And what I'd like to show you is how the redox properties of the iron catalyst influence the selectivity and the performance of the catalyst. What we found out is that controlling the iron carbide formation is very important to the selectivity of the catalyst. Now, how does this iron carbide forms during catalyst activation? This is iron oxide being treated with hydrogen and CO at 1 atmosphere. This is just a temperature ramping. At the lowest temperature, first what one can observe is the CO adsorption, after which comes the carbide formation phase. At higher temperature yet, some excess carbon starts building up in the catalyst and on the surface. And I'm going to show you what is the role of that. Overall, I can tell you in advance that this is something we want to avoid. So we like to make the iron carbide phase that we say is important to catalytic activity and selectivity. We like to make it in a controlled fashion and do it at temperatures where the process is very, very controlled. One way of achieving this is by using a metal promoter that is going to reduction of the iron oxide and therefore promotes the formation of the carbide. So this is one example where cobalt is used. As you can see, the onset of reduction by having cobalt present in the precipitated callus reduces the temperature that is required for the reduction. Now, I claimed before, and I'm going to show you the data, that having iron carbide present as opposed to the oxide is important. First of all, what I'd like to make a statement is just so that the process can be better understood. There are many different effects are at play. Is that based on differential reactor studies, it is clear, and I think that by now it is very well accepted, that both in the iron and cobalt Fischer-Tropsch process, the primary hydrocarbon product is the olefin, and that olefin can be reabsorbed or even before desorption can be hydrogenated. So it is important in a way if one wants to make, say, olefins, which iron callus can be good at. If one wants to preserve that, then we have to make sure that that olefin can get out from the pellets, and that's where the excessive carbon deposition can come into the picture, because that can block the pores, make them smaller, and then therefore can assist in retaining the olefin and making the product overall more paraffinic. Now, on another aspect, when we compare a callus that is made sure that it's all carbide, the gray columns show the product selectivities obtained with a callus that was made by laser pyrolysis of iron carbonyl and ethylene. So it is all just carbide, no oxide present, versus another callus preparation where the active callus is made from the oxide. You can see that the olefinicity of the product made with the carbide callus, the pure carbide phase, is higher. The C5 plus selectivity is somewhat also higher, while methane selectivity is lower. Now, the next example, I'm going to show you how the different callus composition then come into interplay with the process. If we investigate the phases that are present in a slurry versus a fixed bed reactor, what we find is that the starting material is the oxide, and then we take the spent callus from a slurry reactor showing the carbide only present, while in a spent fixed bed reactor we see both the carbide and the oxide on the top of the callus bed, and it's mainly the oxide on the bottom of the callus bed. So if what we are claiming is true, that when we have oxide present, then we're going to have lower C5 plus selectivity, and we are going to have a less olefinic product, then running the reaction in slurry versus a fixed bed should indeed show this difference. So the next slide is then showing exactly just that. I plotted here, or taken the plot from the paper of the product olefinicity for the fixed bed reactor and for the CSTR. And as you can see, indeed, the olefinicity in the CSTR overall is higher. And that correlates well with the fact what we found in the dispensed callus, that it was mainly the carbide, while the C5 plus selectivity in the fixed bed lower than in the CSTR under otherwise very similar conditions. I'm going to change subject and move over to the cobalt catalyst. And at different symposia at this meeting, we already heard quite a bit about how the process interacts with the cobalt catalyst, how the cobalt catalyst can be oxidized at high conversion, and how the activity can change in overall. So if we now have a fixed bed reactor versus a backmix reactor, where the backmix reactor is exposed to essentially the exit conditions, we again would see some interplay between the redox chemistry of the catalyst and how then the catalyst performs. On the left-hand side, I show you some recent data when we were using an essentially differential fixed bed. The conversion was running around 12% only, where we did some isotope transient kinetic switches. This is the work I mentioned we did with Chuck Mings and Chris Bartoli. The fresh catalyst, I plot here the activity, the number of sites, the activity in converting the CO and converting the surface carbon, and the number of active sites. I'm going to reference everything against the fresh values. I have to mention, I guess you're all familiar with this, but all these values are obtained in situ. There is no ex situ characterization needed to obtain these numbers. Then, just to mimic the backmixing or high conversion, when we make water, the co-feed water, in this case 4 atmospheres. I don't show here how the turnover frequency for CO is changing, because we did some other parameters, CO and hydrogen partial pressure changes, and it's going to affect it. But interestingly enough, it's not seen to have an effect on the turnover frequency of the surface carbon. So it's kind of an indication of what is happening with the catalyst. Indeed, as we go back to dry conditions, we are carefully matching at this point the conditions of what we had at the beginning of the experiment. Conversion, partial pressures, everything is the same. So there could be no effect on inventories or reactivities of the reaction conditions, because they are the same. What we see is that both the CO, the adsorbed CO, and surface carbon reactivities are lower after water co-feeding. Now, I need to point out that there's another transient kinetic investigation done at lower pressures by the Sintef group led by Professor Ullman. They found that there was no site activity change. It was a number of sites that changed in their reaction, and we are in an intense talk about what could be the reason for that. But nonetheless, this is what we found. Now, at this condition, we measured the number of CO adsorbing sites. That didn't change a whole lot. After that activity check, we start co-feeding higher partial pressure of water, in this case 8 atmospheres, and we see a further reduction in the turnover frequency of the active carbon. Go back to an activity check, and what we see is that now at this high water partial pressure, the cobalt sintered. It was a very rapid event. It was surprising because notice that we carried out a whole bunch of changes at 4 atmospheres, and we didn't see this sintering process. So this is apparently something that WAR is able to facilitate the sintering of cobalt. After that activity check, we did a re-reduction, and as one might expect, re-reduction is not going to redisperse the cobalt. We don't see a change in the number of sites. However, we recovered the lost site activity. So the end of the long long story is that if we have conditions where the catalyst is going to be exposed to this high conversion condition, that is where a lot of steam is present, then there is going to be an impact on the catalytic activity. And indeed, what we found is that as we changed the backmixing property in the slurry reactor, we see a change in the overall productivity. The iron catalyst seems to be, even though it's less active, seems to have no sensitivity for that. Though, of course, we know that iron catalyst is going to shift the ore that we make. Now I'm going to move over to another subject in the cobalt field to see how we can use, how we can design catalyst that is going to have higher activity, higher selectivity. What can we do to make a catalyst that is more advantageous? The first thing we wanted to find out is if we could influence the activity of the catalyst by coming up with some clever combination of support and cobalt. Can we change the site activity of cobalt by using different supports? The early work that was done in an integral reactor by Enrique and his group suggested that there is essentially no support effect and the reaction is not structure sensitive. That's why the activity of the catalyst is essentially proportional to dispersion and is independent of the nature of the support. And it is true both for ruthenium and for cobalt. Now there is some variation still, and we were hoping, we were guessing that maybe that variation comes from the fact that these dispersion numbers were obtained ex situ. What if the dispersion under reaction conditions is changed because of back oxidation? The other processes I mentioned before. So we decided to look into this issue using the transient kinetic methods whereby we can obtain all these characterization parameters in situ. So if the catalyst changes, we should be able to pick it up immediately and normalize against those changes. What we found is that although there is some variation in both methane selectivity and turnover frequency, as we tested different catalysts on silica, titanium, and alumina supports, there is no correlation between the support and the activity or selectivity we observe. We presented a paper in Toronto, and sometime soon we're planning to submit a paper to the Journal of Catalysis on this. What we found is that it's really not the support. We don't know exactly what is influencing the overall outcome, but it's not the support. It's more like how the surface inventories build up on the reaction conditions that is going to determine the selectivity and the turnover frequency. Now, the conclusion after all this work is then that we cannot really have a superior catalyst by playing with the support or playing with dispersion. I don't want to say, though, that the support has no effect on the overall catalyst performance, because these are all initial activities. The catalyst is going to age, and the aging process is going to depend on the support. Because you may be familiar with the papers that show that alumina and silica both, under hydrothermal conditions, can make, for example, mixed oxides. And in order to mitigate those deactivation processes and enhance the activity of the catalyst, a very wide range of additives have been patented to higher stability and higher initial activity. Now, on another aspect, so we cannot influence the catalytic activity or selectivity by changing the support. However, we found that by simply having different, first initially just having different particle size seemed to somehow impact selectivity. So we wanted to understand what is the underlying reason. And this is the work that Enrique and his group did during the late 1980s. And what they found is that they found that the diffusion within the palate, this is now intra-palate diffusion, can significantly influence the selectivity of the callus. Diffusion and diffusion length and side density, they all interplay, and for that they built a model in which there is a chi factor, and the chi factor essentially incorporates all the callus properties that are related to how they're going to influence the interplay between the transport of the feeds into to the sides and the products out from the palate. The model has two components. One that describes how describes the regime where the restriction on the product transport plays the dominant role. That's on this side with the lower chi values. When the particles are larger, as you can see, the pallet size is on the second order. It has a big impact on the chi value. On larger particles, it is the delivery of the reagents, the CO and hydrogen, that is going to influence selectivity. Essentially what happens is that CO is a slower diffusing molecule, and at the reaction site, because of diffusion limitation, the effective CO-hydrogen ratio can be lower if the particle restricts the transport. Now, once we know this, we can start playing with the model and come up with some designs, some callus designs. And what I'm showing now is callus designs for callus that are large, for fixed bed application essentially. These are just playing with numbers first, and then we're going to try to come up with some methods of implementing. Essentially, the left-hand side graph shows that if we change the thickness of a rim, when we have a dense particle, and then we put just the rim of cobalt on the outer sphere of that particle, and we choose two different thickness, then the selectivity of a thinner rim is going to be better than a thicker rim. And the same is true eventually for the CO conversion. You can play this game by using a hollow pellet that is longer, more cylindrical, or shorter, and the effect of that sort of changes based on the model would play out similarly. Now we need to, however, we need to make these rim callus. The conventional callus preparation uses incipient wetness, and that incipient wetness is going to deposit metal all over the callus bed. Somehow we need to restrict that, and the solution is to use molten nitrate salt. This is the way how it was done in the lab. The molten neat cobalt nitrate was filtered through a packing of the support pellets, and the high viscosity of the nitrate limited the penetration depth. The excess was just filtered away, so it didn't have a chance to impregnate the pellet throughout the impregnate the cobalt throughout the catalyst pellet. And I show you now how the prep then looks using this method. On the top is the catalyst made by incipient wetness. This is just a simple microscopic image of a cut of a catalyst pellet. The cobalt is nicely evenly distributed throughout, while when the molten salt is used, the cobalt is loaded on the surface. Now because the cobalt now is not in solution, it's a molten salt, the concentration of cobalt in that liquid is higher, so a higher side density can be achieved, but it's all on the outer surface. What happens, we promise some benefit by going all this trouble. So let me just first point out on the right-hand side that if now we take samples that are fine powders, so they don't have the benefit of trapping the primary olefins and reincorporating them and growing them, or having the evenly impregnated pellets where we have transport restriction of the feed. In both cases, the C5 plus selectivity is lower than with the ring pellets. So indeed, the fundamental understanding applied to the catalyst design can help the selectivity of the catalyst. On the left-hand side, I show you some smaller particles, because I was saying that this is really important when you go to larger pellet sizes used in fixed bed application. We believe that there is some benefit to having the rim loading even on smaller particles. The reason for that is that with very high loading on smaller particles, it still can have some diffusion issues, and also another factor that is not in the model, but we believe is important. When we load the cobalt in a ring fashion, it also helps dissipating the heat. Now with some further modifications and refining the activation procedures, now we managed to make catalysts that are highly resistant to attrition and chemical disintegration. But all the fundamental learnings really helped us a lot to get there. And what happens when we now test all these ideas, not just on the bench, but in the pilot plant? And this is the example I'm showing you now. This graph shows the overall conversion. The first stage conversion level maintained, and then at one point we started 2 reactors back to back. This is a process demonstration result. The target conversion level was on average 95%, and indeed we managed to stay within that band, while the yield, the selectivities, were also on target. Now finally, Rocco Fiato is the principal author who first signed up, and is a staff person. These staff people like to play with diagrams, so he made me put this up. This is a commercial. He wanted to convey that at ExxonMobil we not only have the fundamental research, but we also have the ability of carrying it through commercialization, and we have the resources all in-house to do just that. Thank you. And before I would that is, the question is how the economics of the process changed while we were making all these advancements. In a dollar per barrel figure, unfortunately, I know it was substantial. We had at one point the $5 per barrel challenge, stuff like that. But how the economics changed, I honestly tell you, I don't know. I'm in the far end, the research side, and I'm not privy to the economic